So in today's discussion, I would like to introduce you to a new term. Most likely it's a new term for you. It's called the transfer characteristic. So let's learn what a transfer characteristic is. So the transfer characteristic comes up very frequently in electronic circuits, and it's very similar to the transfer function we discussed or the gain we discussed. So it's something very similar to the gain of a circuit. So essentially what we mean here is, if you have some circuit, and you have some inputs, let's suppose, you have some output, then your transfer characteristic is nothing but V out by V in. So transfer characteristic is just the ratio V out by V in. If you remember our discussion of filters, there we had something called the transfer function. So I said that the gain of the filter is nothing but the magnitude of the transfer function. So you might ask, how does transfer function differ from the transfer characteristic? Well, transfer characteristic, usually we would like to evaluate in the time domain. Transfer function, if you remember, it was the transfer function, if you remember the definition, it was h of j omega. It was something like that. V out of j omega, V in of j omega, and we said that this h of j omega is the gain. The magnitude of the transfer function was the gain. So that was transfer function. And this one is transfer characteristic. The transfer characteristic is more common in electronics circuit analysis. You'll come across the term a lot. So when we are dealing with different circuits by BJTs, MOSFETs, oftentimes we ask, what is the transfer characteristic? So transfer characteristic is V out by V in, and there we are not talking about any Fourier transform, we are not talking about any j omega term. These are just normal voltage values, but essentially these two are trying to do the same thing. They're just trying to relate the output to the input. So if I am given a circuit and I'm asked to find the transfer characteristic, usually there will be a V in, there will be an input, there will be output, V out. So I just need to find out the ratio of V out divided by V in. So the transfer function is, this is by contrast. By contrast, transfer function was exclusively done in the Laplace domain or in the j omega domain or S domain. And then we came up with this particular ratio, and we said that this is the transfer function, and the magnitude of the transfer function is the gain of the filter at frequency omega. So that was from our filter discussion. And now here I am talking about something called the transfer characteristic. So when you just hear the term transfer characteristic, we are typically meaning that what is this ratio of V out by V in? So suppose I have a circuit and I supply 5 volts and my output is 10 volts. Then transfer characteristic evaluated at that point is 10 by 5 is just 2. So normally what we would like to do is we would like to plot transfer characteristic, and plotting transfer characteristic is actually, it's not even the ratio. I should actually make it clear. So the ratio is just of interest, but transfer characteristic is better said, it's just V out. I would make it a little more simpler, V out versus V in. So transfer characteristic is typically a graph that we plot. So most of the times we'll just plot V out on the y-axis, V out by V in. So you can think of it as a ratio. The graph changes a little bit if you plot V out by V in. But here we are just plotting V out against V in. So you have some transfer characteristics. So you might see something like this. So if your V in is some value, so V in is 1 volt, V out maybe, let's say 0.5 volts, and then if V in is 2 volts, V out is 1 volt, something like that. So basically, what we would do is in transfer characteristic, we will plot a graph. So oftentimes the question would be plot the transfer characteristic of this circuit. So when I am asked to plot the transfer characteristic, all I have to do is plot plot V out as a function of V in. So y-axis would be V out, x-axis would be V in. So suppose I have a suppose I have a clipper circuit. So if I have a clipper circuit, that the clipper circuit does something like this. So it clips everything at some 0.5 volts or 0.7 volts. So how would my transfer characteristic look like? The transfer characteristic would be V in, V out. This point should cross the origin. 0.7 volts. So this, if I see this transfer characteristic, then I can readily say that this is a clipper. Why? Because if my V in is below 0.7 volts, so this is 0.7, so this is 0.7, and this is 0.7. So what I'm saying is that this is a clipper with a diode that has a barrier potential of 0.7 volts. How can I say that? That's because if I look at this transfer characteristic curve, if I look at this curve and see what happens when I put certain magnitude voltages. So if my voltage is below 0.7 volts, then my V in is exactly equal to V out, because it's a slope with a slope is 1. So this line, this straight line has a slope of 1, which means my V in is equal to V out. So this particular graph means that V out is equal to V in if V in is below 0.7 volts, and V out is equal to 0.7 volts if V in is greater than 0.7 volts. Exactly what happens at V in is equal to 0.7 volts is more of a question of convenience. So you can think of it as still, because anyway, your at 0.7 volts, V out will be 0.7 volts for sure. So that does not make much of a difference. But the point over here is that by looking at this graph, you can immediately say that say what value of V out you would receive, what will be the output of a circuit for a given input. So that is that is our that is the benefit of the transfer characteristic curve. So here, if I have, so this one is basically, if my V in is like this, so this is my V in, then V out would be just whenever my V in is below 0.7 volts. So let's suppose this is 0.7 volts. So whenever my V in is below 0.7 volts, then V out is exactly equal to V in. So this value, something like this. So this is my V out. So this is nothing but a clipper, right? So by looking at this particular transfer characteristic curve, I can say that this is the transfer characteristic of a clipper. Any clipper will have this sort of a transfer characteristic. So if it's an ideal clipper, then what would the transfer characteristic look like? So this is a clipper. So this is a clipper with barrier potential 0.7 volts. Clipper with a diode that has a barrier potential of 0.7 volts, to be very precise. The clipper itself doesn't have a barrier potential. The clipper just has a clipping level. But this is basically a clipper with a diode that has a barrier potential of 0.7 volts. Now, if I have a clipper with an ideal diode, so if I have a clipper with ideal diode, then what happens? all the value, I'll get the same V in and V out if V in is below 0 or V in is negative. But if V in is positive, then everything is clipped. So my V out is 0. So this is V out by, sorry, V out. This is V in by V out. So this is my transfer characteristics at this point 0. So for this is nothing but an ideal clipper. Clipper. Yes. Any question? If you're trying to ask something, I am unable to hear you, unfortunately. Okay, so if there's a question and you are unable to, yeah, please.
Sir, sir, what is the difference between ideal clipper and non-ideal? What is means of that?
No, but that is why I said ideal clipper means a clipper that is using an ideal ideal diode with no bias voltage. So that's what I meant. So basically, let's take this word back, because you might try to use the word ideal clipper. There is no such thing as an ideal clipper as such. I mean, a clipper that is using an ideal diode, and for this particular example, the bias DC bias of the clipper is 0. So that's what we mean. So basically,
for the diode, only first approximation is applied.
Yes, a
Let me
diode
go.
first approximation. Yes, yeah, you can think of it as like that. So only a ideal approximation is applied. So this is ideal clipper in that sense. So okay. So that's the thing. But you could have a diode for which you are applying the second approximation, fine. But you could actually add a DC bias of minus 0.7 volts to make the diode have the exact same transfer characteristic that we are calling an ideal clipper in this case. So in any case, let's get this thing clear. So what ideal clipper, this particular thing, there is no such thing as ideal clipper. I just was kind of concise with this name, but the actually point is a clipper using an ideal diode and no DC bias. So if you remember, there is this thing called the biased clipper, where I could add a DC bias to increase or decrease the clipping level. So that's a DC bias. So for this particular diode, we have no such thing. So we have, so V out is equal to V in if V in is below 0, and 0 if V in is greater than 0. Okay, so this is your V out. So if I try to plot it, if I have something like this, this is my input, my output would be this is V out. Okay, so basically the point we need to that point you need to remember is that the characteristic function or the transfer characteristic, I'm sorry, the transfer characteristic actually gives you a very nice way of representing this input-output characteristic instead of drawing all the sinusoids. So here is the problem in drawing these sinusoids. Sometimes you may not be supplying a sinusoid to the waveform, to the circuit. You might be supplying a triangular wave. You might be supplying a square wave. You might be supplying something absolutely arbitrary. But if you know the transfer characteristic, then from there you can immediately say what the output would be. So all I need to specify for this particular circuit is this transfer characteristic. So from the transfer characteristic, I already know that for this specific ideal situation, if my input is like this, then my output would be just these lower clips. If my input is something like this, then my output again would be just wherever this thing went off. Okay, so something like this. So basically, all this can be inferred just by looking at the transfer characteristic. I don't really need to specify everything for every input. What is the output? I don't need to tell that. As long as I am able to tell you that for this particular voltage input, I get this particular voltage output. So from that knowledge alone, I can say for sure what my output would be for any given arbitrary waveform. So that is the benefit. Okay, so this is okay. So this is the transfer characteristic. Is this clear? If there is anything, we can get it clarified right away. Otherwise, we will just try out a question. So the question is, plot the transfer characteristic for the following circuit. I'll draw a circuit for which we will be plotting the transfer characteristic. And what is the circuit? The circuit looks like this. I have a VI. I have a 100 ohm resistor in here. I have a diode like this here. And I have a 2 volt voltage. And there is an output. And I am told that this diode has a VK of 0.7 volts, knee voltage. Some people also call this knee voltage V. Different terms people use. So there is another term like this. But anyway, it will become clear when your question clearly mentions. So if you see this VK, then it's the knee voltage. Sometimes there might be some other voltage. Someone might call it the barrier potential. Either way, you know that there is this threshold of 0.7 volts that need to be crossed. So that's very clear. And we will be dealing with silicon diodes. So that term will always be 0.7 volts. So that again does not cause much confusion. Also, if you're using a germanium diode, just in the rare case, then you'll see a 0.3 volts. But anyway, if you see VK 0.7 volt, but some other term called 0.7 volts, you'll probably be knowing that this is indeed a diode with a barrier potential of 0.7 volts. Okay, so now coming back to this question, I want to plot the transfer characteristics. So what I want is a plot of VI, V0 with respect to VI. So sometimes it's not very clear what is the input, what is the output, but normally we would draw the input at the left, output at the right, and VI, whenever you see a VI kind of thing and then V0, so it becomes clear implicitly that input is VI, output is V0. So this is a very standard notation. Okay, so this is what I want to plot. This is the transfer characteristic. So this circuit, any guesses what this circuit is? What do you think this circuit might be doing?
Clipper.
Yes, exactly. So this is a clipper circuit. So how do I know it's a clipper? Because I have a diode, I have a voltage, I'm taking my voltage at V0, but if whenever the diode is shorted, whenever the diode is conducting, then all my current goes to this way. So basically, I'll have the diode is not giving anything, contributing anything to the output voltage. So I'm going to get a steady voltage of 2 volts plus whatever the barrier potential is. But if that sort of reasoning does not fly with you, if you feel that this is a little vague, what you could always do is you could try redrawing the circuit as before. So whenever you are in doubt, redraw the circuit. Redrawing the circuit, we get something like this. So you have a VI over here, or rather I will not give plus minus, I will just say this is VI. Maybe let's do the plus minus, but keep in mind that plus minus does not mean that it always has to be.
Screen is not visible now.
Sir, Madan has started sharing something.
Yes, I think he is sharing his screen.
Okay. So let's. So if somebody is sharing, please stop the sharing. I would go back to sharing mine. So is it visible now?
Yes, sir.
Okay. So we were at this point. So we had this original circuit that, as you have rightly guessed, is a clipper. But sometimes it may not be very clear in some cases. So let's redraw the circuit. So let's not suppose. I mean, it's given that Vi is a voltage source, and that voltage with respect to ground, I can write as a give the symbol of a voltage source. So I write Vi in that manner. Then I have a 100 ohms resistor in here. Then what I have, this particular point A, let's call this point A. This node A, from node A I have a diode, and the diode's P terminal is connected to node A. So I have to be careful about uh, these specific polarities. Okay, so the diode now will be pointing downwards because node A, if you look at this particular node A is connected to the positive P terminal of the diode. So I have to make sure that I am doing the exact same thing in my drawing. And then what I have is a 2 volts source. And this node A is directly connected to output. So this is right. So the first circuit and the second circuit are both equivalent. So this is important. So as long as I am drawing the correct equivalent circuit, then only I will get the correct result. If I make some mistake in drawing, especially the most common source of error is assigning these polarities. So you see a diode pointing upwards, but the point over there is that the diode is pointing upwards, sure, but its P terminal should be connected to the node A. And that's what I had to ensure. Similarly, the N terminal of the diode is connected to a 2 volt source, 2 volt, the positive 2 volts. So if the equation had said minus 2 volts, then it would have been the other way around. But now I need to make sure that the 2 volt source is connected to the N terminal of the diode. Also, we need to remember that whenever I see a 2 volt or Vi, any such term, so let's see this 2 volt, let's see a Vi, all these terms, they mean that that particular point has a voltage Vi or a voltage 2 volts or some other voltage with respect to the ground. So that is why I can draw my 2 volt source in this manner or my Vi source in the manner that you see in the screen. So this is my circuit. And this one, this diode.
Sir, your mic is muted.
Okay, so let's try this again. So we have this circuit. So now what I can do the circuit, I can simplify further by saying that I have Vi over here, 100 ohms. And I draw this circuit in a way that it's 0.7 volts and plus 2 volts, 2 volts. So what I did was, now I have an ideal diode in here. ideal diode. So basically what the way I did was, I took this practical diode that had a barrier potential of 0.7 volts. Now I am replacing that practical diode with this series combination with an ideal diode and a 0.7 volt source. So this is our second approximation. If you go back to our old notes or into the textbook, you will see that this is our second approximation. So we draw it like this, and finally everything else remains the same. So given this, I can simplify this further. Ohms. I have an ideal diode, this is ideal, in series with 2.7 volts. So this is my final circuit. So clearly this diode would conduct only when Vi exceeds 2.7 volts. So, and for Vi, so if Vi is below 2.7 volts, in that situation, what you have is an open circuit. So you have Vi, 100 ohms, is an open circuited situation, 2.7 volts. It does not matter any longer what this voltage value is, because we are anyway open circuiting the whole thing. V0. So what you really have at the end is V out, V0 is equal to Vi. So if Vi is below 2.7 volts, I have output exactly equal to my input. But if V in is greater than 2.7 volts, then I have V in 100 ohms. I have a short circuit in place of the diode, 2.7 volts at the output, right? So this is my situation if V in is greater than 2.7 volts, and this one I can clearly see that V0 is 2.7 volts, because V0 is just the potential difference between this point, the one I'm pressing here, and the ground. So this potential difference will be exactly the same as V0, because this wire and this wire, these two wires are just conductors, so there cannot be any potential drop over here. So my V in is clearly V0 is clearly 2.7 volts. So V0 is 2.7 volts. So what this circuit does is it clips everything at 2.7 volts. So if my input is something like this, my output would be same thing but clipped off, something like this. So this is 2.7 volts. All right. So now how do I plot the transfer characteristic? So the transfer characteristic is this is 2.7 volts and this is 2.7 volts. Okay. So what we see here is that the transfer characteristic is a straight line for the part below this below 2.75. I mean, it's a straight line with a slope 1, and then it's a flat horizontal line for values of V in greater than 2.7 volts. So I just write down V in and V out. So this is V in, V out, or V or whatever you write. But this is my transfer characteristic. So this is how you plot the transfer characteristic. And of course, if you have a negative diode, then the things would become different. So you'll see how to plot these things. So basically, if you have a negative clipper, for a negative clipper, what you have is something like this. This thing should go to the origin, right? It'll clip at some negative value. So this is a negative clip. Okay, so this is output, V out. This is input. Okay. And what might a clamper transfer characteristic of a clamper might look like? So the transfer characteristic of a clamper, positive clamper, let's say, positive clamper. So what does the clamper do? The clamper, what it does is the output voltage of the clamper is the input voltage plus this fixed value, right? So that fixed value Vp was the mean of this. So the input goes from minus Vp to plus Vp. So input, so V in was something like this, plus Vp and minus Vp. So the clamper, what it does is it will shift this positive clamper will shift this waveform up by an amount equal to Vp. So in this case, if Vp were 0, then I would just have this line, right? V in, V out. But of course, Vp is not 0. So what I would have is something like this. Is this correct? So basically, what I have is a straight line, but it has an intercept which is greater than 0. So it's just shifted upwards. So whatever V in is my value is, it'll just be shifted upwards. Okay, so this is my this is my transfer characteristic of the clamper. So I hope transfer characteristic is clear now. And let's look at one more example, but this does not have to, this has got to do nothing with transfer characteristic, but another type of diode circuit. So again, these circuits, what we are currently doing is we are just trying to get familiar with different types of circuits, their representations and how to analyze them. So here we are asked, we are given a circuit that looks like this. You have a 2 kilo ohm resistor. V out, and there's a current I flowing. There's a 1 volt here. There's a 3 volts here. And we are asked to find out, okay, there is another 3 volt here. And then we are asked to find out what is the value of I and V out. So the question is, what are I and V out? This is the question. So we want to find it out. So again, you could look at this circuit and see what is the voltage developing across each of the diodes and see whether it's a what do you say? It's an open circuited or short circuited state, and that's fine. That's how we would do it. With practice, you don't really go ahead and solve these circuits. You just look at the circuit and then answer the question. But for now, since we are at the very initial stages, I am doing things in a very great amount of detail. So let's take the same approach here. So to see what's going on in this circuit, let's try redrawing it. So basically, let's try to redraw the circuit. And if I redraw it, what I have is, I first draw this 3 volt source. This is a 3 volt source with respect to ground. So let me draw this 3 volt source with respect to the ground. Then I have a 2 kilo ohm resistor. There's a current flowing towards my terminal, the output. So that would be my V out. Okay. And then from V out, and the meeting point of V out and the 2 kilo ohm resistor, somewhere I have one diode pointing downwards because the N terminal of the diode, P terminal of the diode is connected to this particular node. Let's call it node A. Let's node A. And then I have a 1 volt source, and then 1 volt, the positive of the 1 volt is connected to the negative terminal, N terminal of the diode. Sorry, this is not D1, and this is 1 volt. And then another D1 plus 3 volts. So this is basically V out. Okay, so this is what I have, and I am asked to find out what V out is. So to find out what V out is, we first need to find out whether the diodes are conducting or not. If both the diodes are not conducting, then its V out would be just 3 volts, right? So if you find out that the diodes are not conducting, so none of the diodes are conducting, then you have you don't have to do anything. You just look at this particular circuit and you answer the question. But now let's see what's going on. Here, what actually happens is that this diode D2 is not conducting because there is a 3 volt source biasing the diode in the connected to its P terminal, N terminal, and towards the P terminal I have this 3 volt source providing some voltage, but then whatever voltage this provides, this flows through the current, whatever current this provides, it flows through this diode D1. So I have a diode D1 that is in the conducting state because I have a 3 volt supply here. I have only 1 volt opposing bias. So I have this diode D1 conducting. So in this diode, when the diode D1 is conducting, you know that diode D2 will not conduct because at this point I can have nothing, I cannot have anything greater than 3 volts, because in order to make diode D2 conduct, I need to make sure that the potential at this point, the potential at the P terminal of the diode should be greater than the potential at the N terminal of the diode. And that's not possible because at the N terminal of the diode, I have a 3 volt positive potential. Whereas the P terminal, all I have is this 3 volts supplying me something, but whatever voltage was there, everything actually flew through. All the current is traversing through the diode D1. So basically you have a 3 volt potential and there is another potential drop across the 2 kilo ohm resistor. So eventually at the P terminal of the diode D2, you will not get any potential higher than potential higher than 3 volts. So as a result, D2 will not conduct, whereas D1 will conduct. So now what I have is 3 volts. So what I have is D1 is conducting, D2 is not. So this is my situation of these two diodes. So my circuit, eventual circuit would look something like this: 3 volts. So let's not draw the diode here. I'll just say that this is a short-circuited diode. Plus 1. And this is here. This is 1. So what I have is some current flowing. What is that current? That current is the total voltage in the circuit, and that voltage is 3 minus 1 is equal to 2 volts. And what is the resistance? That's 2 kilo ohms. So that is 2 kilo ohms. So that is 1 milliampere. So I have 1 milliampere current flowing through this circuit. So that is my value of I. So what is V? What is V out? V out is 3 volts minus whatever voltage drops across this thing. But you don't really need to do that, because here you see that this particular term, these two terminals, So if you look at these two terminals of the 1 volt source, obviously the voltage drop across these two terminals will be 1 volt, and that will also be equal to V out. So basically I have V out equal to 1 volt. Okay, so this is how I can do it. But I could have actually done it in some other slightly more roundabout manner as well, as I was about to do a while ago. So I was about to tell you that V out is the supply voltage 3 volts minus voltage drop across the resistor, which means it's 3 volts minus 2 kilo ohms times 1 milliampere. That's 3 volts minus 1 volts. That's 1 volt. Okay, so this is, so sometimes you have to do these things, but here the equation is actually rather straightforward. You don't really need to get into all that trouble. You already see that V out is just the two terminals of that 1 volt source. So these are the same terminals. So in circuit analysis, it's always very important to keep in mind that these things are the same terminals. These two terminals are the same because this is just a conductor. So this is a conductor, so no voltage drop in there. So this is just for our visual convenience that I am drawing it like this. So in the real circuit, you might just, this conductor, this part may not even exist. This part may not even exist. You will just put the voltmeter across these 2 points, across this point and this point. So basically this is important. Just because I see a wire doesn't mean that something is changing over the wire. So this is how we do this analysis. Now, one thing to keep in mind is that sometimes these analyses get a little harder to keep track of, because sometimes it's not very clear whether the diode voltage is positive or negative, because it's not like your resistive circuit where you could do an analysis and you can say for sure what voltage is at what point. Here you have circuits. If the voltage is something, then the circuit behavior changes. If the voltage is something different, the circuit behavior changes. So in your analysis, in order to do some sort of a loop analysis or mesh analysis, you have to make the judgment, is the diode open circuited or short circuited? Because if I do a mesh analysis, assuming an open circuited diode, it's something different. If I assume a closed circuited diode, then it's again something different. So we have to apply our judgment, but we will be doing a lot of problems, and in the process, we will learn more about how to apply these judgments. Most of the times, you look at a circuit and you have a guess, and you, based on that guess, you try solving certain, do a couple of steps, and you see that okay, it's all working out fine. There is no contradiction anywhere. So at that point, you know that okay, your approach is correct. Sometimes you end up in a contradictory situation where you were assuming a diode to be open circuited, but then you are seeing that the voltage across this diode is 0, or there is some current flowing through these 2 points. So these things happen, and then you will know that okay, maybe you made some mistake in your assumption of open circuit or closed circuit situation of the diode. So this is very typical of any diode analysis. We will be doing problems, and then we will know more about these things, how to make these judgments. But anyway, for today, we are not going to do any more problems because there is not enough time. We just have 8 more minutes, and then I don't want to start another. Okay, so in terms of this problem solving session, we will stop now. And do you have any questions? Okay, so if no questions, then we will stop here. So today will be a slightly shorter class. We just had, we still have 8 more minutes, but I don't want to keep you waiting. You can, if you don't have any questions, then we're all.
Sir?
Yes.
Sir, I have a question related to another topic, that is in RLC circuit, the value of for the
Yes.
the value for the gain function, that
Yeah.
H in the RLC circuit, sir, while solving for it, in the formula we are writing that R by R plus J omega C
Whoever is muting,
J
Pooja, please
omega.
don't do.
Sir, actually someone is muting
Yes,
constantly.
I know. Please don't do this because I know this problem, and I was trying to put some trust in people. So there is a way I can make everyone attendees and not presenters. That way nobody can mute. So I think we'll have to do that, unfortunately, because I usually don't like to start with the default assumption that people are going to be troublemakers. That's why I try to be nice. I try to start from the assumption that everyone would be nice. But yeah, if there is something of this sort going on, then we'll definitely have to take other measures. Yeah. Okay, go ahead. Pooja, can you
Yes, sir.
repeat? Yeah.
That H function for RLC circuit, we are finding the magnitude. So in that function, sir, does the arrangement of the capacitor or the uh,
Yes.
of the capacitor or the inductor affect the uh, order or order of the
Right.
WL and 1 by WC in the denominator in that
No.
magnitude?
No, I mean, suppose you have an RLC circuit and you are trying to get the output across R.
Huh.
Okay. So it does not matter whether the capacitor is first or the inductor is first, as long as they are there somewhere. You'll get the same result. You'll get the exact same output.
Okay,
So,
if the
yes.
output is across the inductor.
Yeah, then it will change. So that is the point. I mean, if you have an RLC circuit, it does not
Huh.
matter who's where. You can have RLC, RCL, LCR, doesn't matter. But what really matters is across
Out.
which element you are taking the output. So if you're taking it across R, you'll have some output. If you're taking it across C, you'll have some other output. If you're taking it across L, you'll have yet another output. So that is important, what we are taking the output across. Okay?
Okay, sir, we are now suppose we are taking across the capacitor.
Yes.
Then the capacitor term will be different, and for R and L it will be different.
Yes, for R and L it will be different. So it definitely will be different depending on which element you are taking the output across. So for example, if you think about the older circuits, RL circuit suppose. So if you remember, if I took the output across R, I had a low pass filter. But if I took the output across L, I had a high pass filter. So the circuit completely
Huh.
changed. So that's the same thing happens in this RLC circuit as well. Depending on where I am taking the output, the behavior of the circuit would be different. Behavior of the output. I mean, not actually, I should rephrase it. The circuit would be the same, so the behavior would be the same, but in terms of that output, my output would be different. So the pattern, output pattern would be different.
Okay, sir.
Yeah. Okay. So, any other questions? Yeah. Okay. So if there are no more questions, then we can stop here.